Yes, I think hold on. Cool. Oh, yeah, it's recording. Okay, cool. Um, Hello, everyone. Thank you all for joining us today. My name is Matthew. Joining us from Montreal is Basil. Today we'll be going over transformers, a technology that's helped revolutionize natural language processing tasks, as well as Hugging Face, the one-stop library that provides any tools you need to design and fine-tune your own transformers in your own projects. So to begin, we'll start by exploring transformers more theoretically, discussing their foundations, their benefits, their wide range of applications, explore their various components, as well go over a few examples. This should provide a pretty foundational level of understanding of transformers. So next we'd be able to move on to something more practical. We'll be shifting to the Hugging Face libraries. There we'll go over demonstrations on how to employ these libraries to use transformers to meet your own needs. For this workshop, we believe it'd be useful for you to have like a mid-level understanding of the fundamentals of deep learning, as this is a slightly more advanced topic. But because it's a more intuitive demonstration, we're not going over like the complex mathematics of it all. So even if like you don't know too much, you should still be fine. And then once we get to the Hugging Face demo, just some experience working in Python is probably good because that's the language we'll be using. And then there will also be a few interactive questions throughout the workshop today. So please join us at the Menti link. There will be a prize for the person with like the most points at the end. It's like a Kahoot style quiz. Yeah, okay, so I think we'll get started. So natural language processing, or NLP, is a major subset of machine learning used to understand text through deep learning models. You've seen examples of this in software like question answering, email filters, predictive text, and the infamous ChatGPT. RNNs, or recurrent neural networks, were the go-to model for natural language processing in the past because they're good at processing sequential information. So sentences as well, they're good at handling inputs of varying lengths, so sentences with different numbers of words. However, RNNs do come with their limitations. They have to process information sequentially, so input needs to be processed step by step. So using the output of the previous step as part of the input in the next step. This also means that tasks can't be parallelized. So on the slide, there's like an abstract example of what an RNN is. It translates the sentence, "How are you?" to "Comment allez-vous?" In French. So you see in the first step, it takes the input for the word how, processes it, and then uses part of that information as well as the input for the next word, are, to process that word, and then so on and so forth, until it starts working backwards to output the word comment in French, and then uses that output as well as the remaining information to output the next word, aller, and then so on again until you have a full sentence. As you can imagine, with longer input, this processing method takes up far more time. So with larger RNNs, they usually perform better than smaller models, but the models can take an unreasonable amount of time to train, sometimes on the order of weeks. So to circumvent this, we can build smaller models that are less accurate but take a more reasonable amount of time to train. So while RNNs were widely used in the past, they have their limits, and that brought upon the need for transformers. So transformers, less cool than the giant robots, but still pretty fun, were introduced in a famous paper called "Attention is All You Need," which heavily relies on something called an attention mechanism, which we'll discuss a little bit later in the workshop. There are a few key advantages to addressing the issues with RNNs that we just talked about. Most importantly, they can handle and train inputs in parallel. So this significantly cuts down on the amount of time that's required to train the models, meaning that larger models with increased accuracy made with more parameters can still be trained in a reasonable amount of time. Next, they're also more capable than RNNs at handling like long input range dependencies. So that just means they're better capable of remembering data points from time steps prior. So transformers were first introduced for sequence-to-sequence natural language processing tasks that you've seen: text generation, question answering, the Snapchat AI, and the GPT models. GPT even stands for Generative Pre-trained Transformers. The original DALL-E 1, used transformers for their text-to-image generation, and was actually used to make the image on the slide. It's kind of small, but it's Baby Yoda on trial for his crimes. DALL-E 2 uses diffusion models, which is a topic that'll actually be covered in another workshop that we'll be having this term, so come out for that. And more recently, the transformer architecture has been repurposed for other tasks. So vision transformers can handle vision input and other computer vision related tasks, and decision transformers were used for reinforcement learning. I'll pass things off to Basil to go over architecture and the Hugging Face demo.
Cool. So yeah, now we're going to be taking a closer look at the transformer architecture. Ooh, Matthew, there's a bit of echo, so if you don't mind, just muting yourself. Okay, perfect. So yeah, now we're going to be taking a closer look at the transformer architecture. I know it might seem a bit daunting. There's a lot of different components here, a lot of weird connections floating around, but no worries, we're going to be breaking it down component by component, step by step, and taking a closer look at each single one and how they come together. So the three main components that we're going to be taking a closer look at are, number one, the input embedding, number two, the encoder, and number three, the decoder. So let's get started. Before we get started, we're going to take a step back and take a look at the general encoder-decoder model that we see a lot in machine learning. It's very popular, and it gets implemented using a number of different machine learning model types. It can be implemented using RNNs. It can be implemented using your regular neural networks. It can be implemented using CNNs, etc. And it basically consists of two models. It consists of an encoder, which takes in your input and extracts the most important information and the meaning from that input. And then the second part is the decoder, which takes that meaning, takes that important information, and uses it to produce your desired output. Let's take a look at this with an example. So say you want to translate a sentence from English to French or English to Arabic. You start with your sentence in English. The goose attacked the student yesterday. The encoder would take that sentence and it would extract the important meaning and information from it. So that would be, yesterday, there's this goose, there's the student, the goose absolutely trampled the student. That's the meaning that you'd want to get from this sentence. And then the decoder would use that information, use that meaning, in order to produce an equivalent sentence, but in Arabic. So in Arabic, that would be cool. So with that in mind, with that out of the way, let's now break down the transformer architecture step by step. We're going to be taking a look at the architecture and each component by using a translation example as we had done previously. So we're going to see how each of these components are used to translate a sentence from English to French. We're going to be starting off with the first major component, which is actually divided into two small ones, but we group them under the input embedding. So, okay, we're starting off with a sentence in English that we wish to translate in French. The first step that we want to do is we want to take this sentence from English and convert it to a set of numbers. The reason being is that models, that be transformers or actually any machine learning models in general, don't really understand English sentences or don't really understand English words or characters or in English in its pure form. They only take in inputs as numbers. So that's what we're doing with input embedding. We're taking our sentence in English, we're splitting it into each of its words, and then each word, we convert it into a corresponding representative vector. The cool thing about these vectors is that they represent coordinates on this what we call an embedding space. So this embedding space is kind of like a grid. Words that have similar meaning have coordinates in the space that are closer to each other. Let's take a look at this through our example here on the screen. So we have a set of words. The words bathroom, toilet, shower, which have a similar meaning, correspond to coordinates that are closer to each other on this graph. Opposingly, lamp, light bulb, LED, etc., are pretty far away from this group, and they're closer to each other. Similar thing for kiwi, apple, pizza. They have their own like coordinates, which are separated pretty far away from the rest because their meanings are quite different. But to each other, since they're all related to like food stuff, kiwi, apple, pizza, they're pretty close to each other. So to recap with like the input embedding, you take a sentence from English, you split it up into each of its words, and then convert each word into a representative vector, which houses information about the word's meaning.
Sorry, I think your sound cut out for a second. We can't hear you.
Sorry, I muted myself on accident.
Oh, there you go. You're back.
Okay. Yeah, second step of input embedding is the positional encoding. So what the positional encoding does is it takes each of those vectors that we had defined for each of the words in the sentence, and then adds more information to the vectors about the position of the word in the sentence. Now, why would we want to do that? Reason being, transformers process each word in parallel. And by doing so, it loses information about where the word is in the sentence, like which words came before it, which words come after it, is it at the start, is it at the end? Information like that, which would be important to understand how this word relates to other words in the sentence. So by performing positional encoding, in this vector that represents the word, you add more information about the word's position in the sentence. Cool. So just to recap what we've done so far, taken a sentence, broken it down into each of its words, and then each word, we converted it into a vector, which houses information about the word's meaning and the word's position in the sentence. Okay, with those vectors, we move on to the next step and the next major component in transformers, and that is the encoder block. So we had previously gotten information about each word individually. Now through the encoder block, we take a look at all the words in unison. We look at all the words and how they relate to each other. And we do this through what is known as the self-attention mechanism. Through the self-attention mechanism, you calculate what are known as attention scores. And the attention score basically represents how strongly related one word is to another word in the sentence. So if the attention score is high, that means the two words are closely related. If the attention score is low, vice versa, it means that the words aren't really related that much. You don't really care about one when you're analyzing the other. This is like further illustrated in the example that we have on the side. Let's take the sentence, black dogs and red cats. If we look at the first word, just the word black, we notice that it's pretty related to dogs since it's the adjective that's describing dogs, but it's not really related to cats or red or and like it's mainly being used to describe dogs. So for the word black, you have a high attention score for the other word dogs and low attention scores for the other words in the sentence. Similar thing for dogs. It's pretty related to black, but it's not related to the other words in the sentence. So attention score for black is higher. Attention score for the other words in the sentence are much lower. Recap once again what we've done. In the input embedding, we've taken our sentence, split it into each of its words, and then analyzed the meaning of each word. And then in the encoder block, we took all those words together and we analyzed how each word relates to the other words in the sentence. Any questions or concerns so far before we move on to the decoder part? Matthew, if you can just give me like a thumbs up because I can't really hear.
Yeah, I think we're good.
Awesome. Okay, So with that information, now we pass it on to the third major component in the transformer architecture, and that is the decoder, which is what uses all this information that we've accumulated about our input, which is like the sentence in English, and uses it to produce the output, which is the same sentence, but in French. So, okay, second. Yeah. What it actually does, like decoder on its own, is it basically takes the input in English, and then it takes whatever outputs the decoder had previously outputted in French, and then predicts what the next word in French should be. So in this example, let's say we have the sentence in English, which is, I ate the apple. So far, the decoder had outputted, j'ai mangé là. Ideally, what we'd want the decoder to output is pomme, which is the continuation of this sentence in order to produce an equivalent sentence to I ate the apple, but in French. And it does so over three major parts. The first part takes in whatever the decoder had outputted so far and calculates the relationships between each word and the word that came prior to it. So it's like relationships between the different words that the decoder had previously outputted. And then the second part is it takes that information about the words that it had just outputted, and it takes additional information about the sentence that we wish to translate in English, combines both of those together here inside the second block, and just to get like relationships between what we've outputted so far and like what we've already, and the sentence that we wish to translate in English, just relate both those together. And then in the final block, it uses that information in order to determine what word should be output next in French. So we're going to be taking a closer look at this last part, the classifier. What it does is it takes that information that I had mentioned about what was previously outputted and the like input sentence in English, combines that information and determines what like word to output next. And it does so by taking all the possible words that you have in French, and then for each one, assigning a probability. It's a probability by like the softmax layer that's being used. But it's basically like a score. The higher the score for that specific word in French is, the more likely it is to come next and to like be outputted next. So let's take another example. Say we have the sentence in English, my name is Jack. And then in French, so far, we've already outputted je. So the word after, like ideally in French would be like je m'appelle. So if we look at like all the possible words that we could be outputting next in French, the word m'appelle would have a higher score. It would have 95%, like it's 95% likely to be outputted next. The word nom, which is ungrammatical to add here, but is somewhat related. It's like somewhat related to the context and like the meaning, its name, has a considerable score, like of 3%, but it's nowhere near as high as the score of this, like m'appelle. Same thing for prénom. And like for all other words in French, they're pretty unrelated to the sentence here that we're trying to translate. So they would have a low score. Like they're very unlikely to be chosen next as our next output. And so yeah, what happens in the classifier, we assign all these scores, their probabilities, like I mentioned, by the softmax function, like softmax activation. And then we sample from these from these probabilities in order to determine the next word that we should output. We take this next word that we should output, and then we pass it back in as input to the decoder in order then to like process it and determine what word should be output next. So some of you might have noticed an issue with that, though, is that the processing happens sequentially. Like in order to output one word, you need to have already outputted all of the other previous words. You need to wait for all the previous words in French to be outputted in order to process it, use it to output the next word, and then you take whatever the next word was, you pass it back in. Like, it's a whole sequential process. So, for example, in this example here, to output the word m'appelle, you need to have already outputted the word je, process the word je with the input, and then use that to output the word m'appelle. And then you take je and m'appelle, you pass it back in, process it in order to output the word after that, which is Jack, and so on and so forth. But the issue with that is that's the sequential processing that we were like explicitly trying to avoid when moving from recurrent neural nets to other methods. So in order to circumvent that, in order to make the whole process parallelizable, we resort to a technique called teacher forcing. So what is teacher forcing? Teacher forcing basically disregards the previous outputs of the transformer. Let's take a closer look at this through another example, which is still a translation. Say we have like the sentence in English, which is, my name is Basil, and we wish to translate it to French. We know, like, since this is a supervised way of training, we know what the output sentence in French should be. It's je m'appelle Basil. Without teacher forcing, what we would do is we would pass in this input into the transformer, and then tell the transformer, okay, output what the first word should be. Say output small, which isn't like the word that we want. That's fine. We use it, we pass it back in as input to the decoder, use that to produce the word after it, which is non, and then pass that back in as input to the decoder, produce the word after that, so on and so forth. But yeah, as I mentioned, this is the type of like sequential processing that we're trying to avoid here. We don't want to like have to rely on previous outputs in order to get meaning for the next output. So what is done with teacher forcing is you slice the target output at different points, and then you feed each of those like prefixes here. Like, let's say we slice it here, we feed everything prior to that to the model, and then we ask it to predict what word it believes should come next. So for this sentence, for the target sentence, we slice it after the first word, je, and then ask it what it believes the word after je should be. And we then slice it after je m'appelle, and we ask the model what it thinks the word after that should be. And if you notice, like when we slice it after je, it produced the word prenom. The like transformer thought prenom should be the word that would be outputted next. But we don't use this output as input back in and ask it what it thinks the word after this should be. We just use outputs from the target. Like each of these tests are independent. They're not really reliant on each other, which allows us to perform all these calculations in parallel. And by doing so, we speed up the training process, which is what we want. Cool. So with that, we finish up the three major components of the transformer. Let's just do a quick recap on the components that we've covered so far. So taking a sentence in English, we split it up into each of its words. We pass it into the embedding, produce the input embeddings, which gives us vectors with information about each word in the sentence. Information about the meaning of each word in the sentence. And then we pass that into the encoder, which gives us information about the words and how they relate to each other. And then we use that information, pass it into the decoder in order to produce word by word the next output, but in the other language, in French. Cool. Now, with that comes the end of the first part of the workshop, like the theoretical part on transformers. Just gonna do a quick Menti competition. If you guys would like, just join the link, just hop on menti.com, pass in the code. It's gonna be 5 quick questions, and we're gonna be scoring based on like how quick you answer and whether you get the answer right or wrong. It's just gonna be like quick revision questions on what I've covered so far. And yeah, like Matthew mentioned, the winner will win like this coveted Mr. Goose plushie. All right, so let's get it started. Matthew, can you just like signal me when everyone's ready? Because I can't really.
Is everyone in? Is everyone good? Anyone still have to get in? Sorry? Okay, just wait 1 second.
Sure.
Okay, is everyone good? Okay, I think you're good to go.
Awesome, sweet. All right, question 1 of 5. Let's get it started. Advantages of transformers over RNNs. Do transformers have simpler design? They perform better than RNNs on smaller data sets? Or are they more parallelized and efficient to train than RNNs? Okay. Yeah, as we mentioned, like transformers process the input in parallel, which makes them more efficient and faster to train than RNNs. Cool. Question 2 of 5. We actually didn't mention this explicitly. I'm just curious what you guys think. So alpha is actually false because RNNs take in inputs in sequence. They take them in word by word. So they already know which word comes in before the other, as opposed to like transformers, which takes them all in parallel, doesn't know which word comes in first, which one comes in next. And so you wouldn't really need to use positional encoders for RNNs. All right. Question 3 of 5. What is the attention score? Is it the measure of similarity between the meaning of 2 words in a sentence? Or is it the strength of the relationship between 2 words in a sentence? Is it just the rating of a Charlie Puth song? Cool. Yep. Yeah, it's just the strength of the relation between 2 words, and it's calculated by during the self-attention mechanism. Question 4 of 5, penultimate question. Well, yeah, so as we mentioned, the transformer assigns a probability score for each word that it could possibly output next. And the probability scores are like defined by the softmax activation function. Then final question. What is teacher forcing? Is it training without calculating attention scores? Is it feeding the decoder the target outputs instead of previous outputs? Or is it using knowledge distillation? Cool. Yeah, so teacher forcing, instead of relying and waiting on the previous outputs of the decoder, just pass in inputs like from the target, which is like the sentence in French. Cool. And yeah, with that, we finish off the first half of this workshop, which is more theoretical side, just getting a theoretical understanding of transformers. Now we move on to a more practical understanding, more practical implementation. We're going to be looking at the Hugging Face platform. Hugging Face platform basically has all the tools that you would need to like load transformers, train transformers, fine-tune transformers, everything you'd need. It's like a really, really cool library and like platform for almost anything in machine learning. They provide you with like thousands of open source machine learning models that you can use. And those are like provided by top tech companies, not just like your friend uploading a model that's like 300 parameters. It's like million and billion parameter models by like Facebook, Microsoft, OpenAI, and such. And they come like different flavors, not just for transformers. They have like ResNets, they have convolutional networks, they have diffusion models, and for like different tasks that you'd want to use. So they have stuff for like image classification, image segmentation, translation, text-to-text generation, etc. And to complement all those like great models, they also have a number of data sets that you can use to train any model that you would have, or like to fine-tune an existing pre-trained model. And similar to the models, the data sets also come in for like the different tasks you need. So you have data sets for image classification, text classification, question answering, translation, etc. And not only that, to complement both the models and the data sets, but they also provide like a number of Python libraries that allows you to use all these resources very easily in Python. So you have the transformers and the data sets libraries, which we're going to be going over in this workshop, which help you load transformers into your like Colab notebook or into your Python scripts. Same thing for data sets. They have stuff for like diffusers, which we're going to be taking a look at in future workshop. And like they have over 140 repositories that you can check. And yeah, they're pretty popular. They're almost like the norm now to use. And yeah, we're just going to be like scratching the surface of the ecosystem that Hugging Face provides. They have a ton of other like features and a ton of other libraries that you can use. So going to be looking at the hub, which stores all the models and all the data sets. Going to be looking at transformers and tokenizers to load them, and the data sets to load the data sets. And yeah, I've prepared a Colab notebook, which goes over how to use Hugging Face. So we're going to be taking a look at that in this workshop. If you guys want to join, you can just type in this link on your laptop if you have your laptop on you right now. Or I think I sent this like presentation to the Discord channel, the workshop Discord channel. So you can open the presentation and open up the slides here, or sorry, the Colab notebook here. Okay. I'm just gonna give everyone a minute. I don't know if anyone's like open up their laptop right now or yeah. So It's the Colab notebook. What we're going to be doing in this like presentation, in this workshop, is we're going to be taking a existing language model, GPT-2, which I'm sure a lot of you might be familiar, like of its bigger brother, GPT-3, GPT-4, which is used in ChatGPT. We're going to be taking GPT-2, but actually even like a smaller version of it, because the original GPT-2 is like 1.5 billion parameters, just impractical to train right now. We're going to take a smaller version of that. And we're going to be taking a data set called Tiny Shakespeare, which has about like 40,000 lines of Shakespeare. And we're going to be, oh yeah, sorry, I forgot to mention. For those of you who don't know what GPT-2 does, it's a text generation model. So you pass in like small input or like a small, I don't know, sentence, and then it basically auto completes that with whatever it thinks like the next output should be. So if you like pass it in a question, it should realistically like answer you what that question is. If you pass it in like a dialogue, it should like I guess respond to the dialogue. If you pass it in like what you're gonna see now, something from Shakespeare, should like almost continue it in Shakespeare style. But we're gonna make that even better. We're gonna take the Tiny Shakespeare that I told you about, like the data set, and we're gonna use it to like fine-tune GPT-2 such that its outputs are now like in the style of Shakespeare. This is like an example of what we should expect to see. So you'd input Hamlet says to be a goose or not to be, and what the model responds back is a continuation of that. So King Richard whoops. King Richard II responds, sir, to be a goose or not to be a crow. Queen Elizabeth responds, I will, sir, to be a goose. See, it's like in the style of Shakespeare. And yeah, by the end of this workshop, you'll be able to, you'll know how to load and process a data set from the Hugging Face Hub. And you'll also be able to load a pre-trained model from the hub and be able to fine-tune this model based on the data set that you just loaded. So to get started, I've actually run like all the code that you see in the notebook, and I wouldn't recommend you running most of it. There's just two that you can like play around with right now, because a lot of these take like maybe 30, 40 minutes to run. Like it's a pretty big model. It's like 88 million parameters. So it takes a while to like train. I wouldn't recommend running it right now. You have the like notebooks. If you wish to, I don't know, play around with it after the workshop, feel free to do so. And yeah, I guess let's just get started. You just want to install the 3 main Hugging Face libraries that we're going to be using in this workshop. The datasets library, which allows you to load the datasets. The transformers library, which allows you to load transformers. Tokenizers library, which allows you to load tokenizers. I'll explain later on what that is. Also, a nice feature about Hugging Face is that it allows you to basically store your machine learning models in like a Git repo that they create on the Hugging Face website, and allows you to like share it with others. So this is one that I created. This is for like the model that we're training in this workshop. As you can see, like if you here, sorry. Let me go back. Excuse me. History commits. Basically, as I was training the model, at every epoch that I was training the model, it would upload a copy of the model weights up to the Git repo and store that, which is useful, like just in case halfway through the training, let's say your, I don't know, server crashes, Colab notebook shuts down, you'd want to keep a copy of the model such that you can go back to it. It all gets uploaded and you can just pull it in and use it for whatever use case you'd want. So yeah, you'd set that up. You just install Hugging Face Hub, and then you need to like pass in an access token. When you run this, when you run this like cell, it just shows you instructions of how to like link your account to the Hugging Face, to the notebook, such that you can like upload your models. And then here we're just going to be, as you guys might know, using a GPU to train your models makes the training procedure like way faster because it allows you to do training in parallel, and that just accelerates the whole process. So here we're just initializing, like not initializing, but just like detecting the GPU device that we're going to be using, and yeah, storing that in this variable such that all the models, all the data we can load onto the GPU in order to make the training faster. And now onto the data sets. Yeah, Hugging Face, like I mentioned, provides a number of data sets that you can use. The data set that we're going to be using is called Tiny Shakespeare, which contains 40,000 lines of Shakespeare plays. You can find it here on the Hugging Face website. And the nice thing about it is that it shows you instructions of how to like load the data set. And the instructions honestly couldn't be any easier. If you go here to use in the dataset library, it just basically gives you the 2 lines that you would need to load the dataset. It's just, you just import the load dataset function, and then you'd use the load dataset, you pass in the name of the dataset that you want to load, and that just downloads it and loads it in for you into the notebook. So yeah, here we just load the dataset. It does the downloading for us, and then the dataset that you see. Also, another nice thing about the datasets that you can find on Hugging Face is that a lot of them come split for like your training, your validation, and your testing. You already have that split done for you, which is pretty cool. So yeah, here we have the train set, the validation set, and the test set. Let's just take a look at an example of what like that data set looks like. You can see it's just a couple of lines of like Shakespeare plays, like Shakespearean style, I guess. You have like one character saying something, another character saying something, and it's all like in pretty old English. So yeah, what we've done so far, we've loaded in our data set. Now it's time to process it. The first step in the process is called tokenization. And tokenization is splitting your text, your sentences, into smaller subunits. When I was previously explaining transformers, like theoretical standpoint, part 1, what I had assumed is when you take in a sentence, you split it into each word, like you just split it word by word. But that's not usually the case. Sometimes you may want to like split it into smaller subunits. Sometimes you want to split it like into a character level, sometimes like a sentence level bigger than that. The tokenizer is what handles that. I guess just to like take a step back, one example of like tokenization. Here, let's say we have this sentence, black cat and black dog. What the tokenizer does is it splits it word by word. So it split it into black, cat, and black dog, each word on its own. And then for each unique word, that's step number 2 of tokenization, it assigns it a unique number. So the word black here is assigned the number 0. The word cat is assigned the number 1. The word and is assigned the number 2. And the word dog is assigned the number 3. So when we take in a sentence, black cat and black dog, this is what the output should be. We convert it from a set of words into a set of numbers. Once again, going back, it's because your like transformers can't take in words and can't take in like pure English. You have to take in inputs as numbers, and this is what the tokenizer does. So tokenizers are unique for each model that you use. Different models would want to split their input sentences differently. Some would like to split them on like character levels, some would like to split them on word levels, etc. And the tokenizer basically, a model has a unique tokenizer for itself. So for our model, like GPT-2, we need to install and load the tokenizer that is associated with GPT-2. And that's what we do here. We just first off import the auto tokenizer, and then we load in the tokenizer that corresponds to GPT-2. So here we pass in the model name, and what this does is it goes to the Hugging Face Hub and loads in the tokenizer that is for GPT-2. So yeah, let's take a look. Let's say we pass in to this tokenizer a certain input. Let's take a look at how it would split it into different subunits. So say we pass in the sentence, Mr. Goose approves of the Data Science Club. The way the tokenizer for GPT-2 would split it is it would split, first take the word Mr. and make it its own subunit with its own number. Then it would actually take the, this is interesting, it takes the dot and splits it in its own subunit, assigns it its own number. Same thing for Goose, approves of the, nice thing, for example, is data science. What it does is it doesn't take this as its own subunit, doesn't take the full word as its own subunit. It splits it into three parts actually. Splits it into data, and then the hyphen, and then science, and assigns each one a unique number. So yeah, what we're going to do now is we're going to use this tokenizer and use it to encode the entire Shakespeare dataset such that we convert the Shakespeare dataset from text to numbers, and we can use those numbers and feed them into our transformer, into our model. And we do that here. Basically what this map function does, or what this map method does, is it applies like a specific function to all the sentences that you'd have in your data set. So like in our Shakespeare data set, each sentence there, it applies the tokenizer onto it in order to convert it from English into numbers. That's what we're doing here. And yeah, the sorry, the Shakespeare data set is pretty big, so I don't really want to input or like output an example because it would take too much space. But you get the general idea. It's just going to take the sentences in English and map them to corresponding numbers that represent the sentence words. Okay. Second part of preparing the data set. What we've done so far, like I mentioned, loaded the Shakespeare data set, converted all the sentences from words to numbers. But something that's like pretty specific to the Shakespeare data set is that like the entire data set comes in as like one string. And you can't really input this like one string into your model. You need to like split it up into smaller groups, smaller batches. And that's what we do here. We split it up into like batches of 128 characters each. I wouldn't really bog you down with the details, but essentially that's what it's doing. So it's taking like the entire thing, just split it down into groups, and it's preparing that data set for us. That's like the final data set that we have that we're going to be passing it into the model. Now, one other interesting thing to note, this process is like a supervised way of training. So we need to think about what the input that we're going to pass into the model is and what the expected label that is assigned to the specific input. There isn't really, like when you're doing text generation, there isn't really predefined labels to the text itself. But to understand like how we're going to do the split, we're just going to take a look at like what we're expecting the model to do. We're expecting the text generation model to take in a small input, like a small set of words, and then predict to us what it thinks the words that follow that should be. So what we do with our data set, each sentence in our data set, we split it into two parts. The first part we pass into the model as input, and whatever the output of the model is, we compare that to the next part, or like the second part of that sentence. Let's take a look at this through an example. Say we have the sentence, Mr. Goose approves of this workshop. The first part of the sentence, Mr. Goose approves of, we pass it into the model as input. And what we ideally expect the model to output is this workshop, like the two words, this workshop. So what we do is, as labels, like as our target value per se, we compare the output of the model to these two words, this workshop. And that's also what's being done here throughout this function. So yeah, now we have our training set, validation set, and test set, and each one is split into a set of like sentences. And each sentence is split into like an input and then the output corresponding to that input. So right now we've processed and loaded in our data set. Now it's time to process and load in the model itself. Like I mentioned, we're going to be using GPT-2, but actually like a lighter version of it. We're not going to be using the full GPT-2 because that's like 1.5 billion parameters. The one that we're going to be using is called Distal GPT-2, which is 88.2 million parameters. For anyone that's interested, Distal GPT-2 was actually trained using a process called knowledge distillation. I've left a link in here if anyone wants to like read more into that. It's a pretty cool topic. But yeah, you can find the model like Distal GPT-2, like I mentioned, in the Hugging Face Hub. And similar to the dataset, the Hugging Face Hub gives you instructions on how to load the model itself. So if you go here, when you click on using transformers, it just gives you 3 simple lines to load in the model. First line is just to load in like the library. Second line is to load in the tokenizer corresponding to that model. And then third line is to load the model itself. And that's like literally all you need. And also cool thing about this like page is that it provides you with additional information that you might want to know about the model, like number of parameters, stuff about like how it was trained, what it could be used for, example of its use cases. Like this is the encoding of the numbers, like it uses full 0.32 bits, which is pretty accurate. That's pretty good. Yeah, so that's like additional information that you might want. And plus, you don't really need to use this model for like using like the other Hugging Face libraries. The whole process that we're going to be doing today is we're going to be using Hugging Face libraries from start to finish, like from end to end. But the nice thing about each of these, like this model and the data set, and like I think also the tokenizer, is that they work with like any other machine learning framework. So if you're a fan of like TensorFlow, if you're a fan of JAX, if you're a fan of PyTorch, you can easily just like take this model and then plug it into your like Torch pipeline or your TensorFlow pipeline or your JAX pipeline. Torch is a like pretty special one in that the whole like Hugging Face pipeline is actually built on Torch, but it's been like abstracted so much, so you don't really. Anyways, I'm just bogging you guys down with the details, but like I said, you can just take these models and use them for in like whatever framework else that you like using. So yeah, we've loaded in the model. We've put it on our GPU, like I mentioned. GPUs are just like allow you to do training and inference much quicker. And then we're going to initialize something called the trainer. What the trainer does is it's like an API that takes in your model, takes in your data set, takes in your tokenizer, and takes in all like the hyperparameters that you have for training. And you define the trainer here, and you can use it to like start your training. You can use it to like train it, your model for maybe like a couple of epochs, a couple of steps, not too much. It just allows the training process to be done much easier. So what we do is we first initialize the training hyperparameters. So here we have like our batch size 32. We want to train our epoch for 20, our model for 20 epochs. We're using the Atom optimizer with weight decay, and this is like the weight decay that we're using, this is the learning rate that we're using. And also these settings are just for us to like push our model to the Hugging Face hub. Like I mentioned here, we want it to be pushed to Hugging Face. We want it to like be uploaded to the Hugging Face hub after every epoch. So we keep like a record of it and we keep like a backup for it. And that's what we enable. With these two parameters, we allow pushing to the hub and we tell it to push it to the hub after every epoch. Yeah, we initialize our trainer. And then the training process is like as simple as trainer.train. That's literally all you need to do. Like if anyone's familiar with, like if anyone's worked with PyTorch, you know how much code you need to write in order to like actually train your model. This is like so simple. Just call train and it does training based on all the hyperparameters that you pass in. So yeah, here we've trained our model for 20 epochs. At every epoch, it gets uploaded to the Hugging Face hub. And then after that, now that we have our finalized trained model, now it's time to like actually use it, actually test it out, actually be able to deploy it. And do that, we use another component called the pipeline. The pipeline just allows you to easily do like inference, allows you to like easily test out your model. So we define the pipeline, call it text generator. And yeah, it's like a text, it's of style text generation, like it does the text generation task. We pass in the model that we have. We pass in the GPU, like the value for the GPU, it's the 0th GPU. And we just say that, oh, like I'm familiar with PyTorch, so I just put in PyTorch. But this honestly doesn't matter. Like it really doesn't for like the later steps. It's just if you want to use the pipeline with PyTorch, like extend it on to like other PyTorch functionalities, or if you want to use it with like your extended TensorFlow functionalities, this is what allows you to do that. Here I just have a PyTorch, you can set it to whatever you want. And now we pass in an input to the model and see what the model outputs. So what I've input into the model is the sentence. Hamlet says to be or not to be. You can define your temperature values. I'm not sure if you guys are familiar with what temperature values are, but it's a score that basically says how much you'd want to randomize the output of the model. So if you set the temperature value to be higher, the output of the model, like every time you run it, is going to be pretty different from the time it ran it previously. It's going to be a bit more randomized. It's going to get a bit more creative than what it's like used to, what other texts it's already seen. And the lower the temperature value is, the more deterministic the outputs of the model are going to be. The more it's going to like just rely on what it had previously seen from like Shakespeare text in order to produce the next output. So yeah, we pass in here, we've created our pipeline. We pass in the input Hamlet to be or not to be. And this is the output that we get. The model responds to be or not to be Ike from the head of France. I'd be the very head of Rome from the head of Rome. And Lucy responds, what then? So as you can see, now the output of the model is more like Shakespeare-esque. It's more in the style of Shakespeare. It's using like Old English. It's writing it as if it's like a Shakespearean play. It's pretty cool. And yeah, that like brings us to the end of this Hugging Face workshop. I've left in a couple of a couple of cells for you guys to test it out. You can just pass in the input of your choice, the input that you'd want. And what it does is it actually pulls like the model that I had previously trained. This federated transformers DSC workshop is like a model that I had previously trained, and it's going to take in the input and produce an output. You can just test it out, try like different inputs, see what it outputs. It's pretty cool. And I've also left a cell for you guys to like maybe test it out, try and load different models of different styles, try and load different data sets of different tasks, fine-tune your models using those data sets. Yeah, just, I guess, get creative with it. They have like really like unlimited resources for you to use, and it's pretty cool to get started with and have fun with. And yeah, that brings us to the end of this workshop. I just wanted to brainstorm where to go from here. Now that we know transformers from a theoretical standpoint, and we know Hugging Face, like how to use transformers in Hugging Face, what can we like do next? What we've covered, like from a theoretical standpoint, is pretty abstracted. We haven't really took a look at the math behind it, and we've like mentioned what the attention score is, but we haven't really like derived how those attention scores are actually calculated. This first link here does that for you, or sorry, like provides a pretty nice guide for you to like explore that. Another thing you can take a look at is the Falcon 40B, which is a new model that was like developed by researchers at Abu Dhabi. It's actually like the best performing large language model as of yet, and it's open source. So you can like pull it from Hugging Face, test it out, play with it yourself. And this is just like a link to a blog post on Hugging Face that provides a guide for you to like use and test it out. And number 3 is transformer agents with Hugging Face. Hugging Face basically released this like functionality of transformer agents. It allows you to like take your transformer, especially like Infinity Stones. You want your transformer to be able to like access internet. It can do that using the transformer agents. You want your transformer to be able to take an input from like Excel sheets or images. It can also do that. So this is like a guide for it. And finally, another resource that's provided by Hugging Face is Hugging Face Spaces. So say you have like, you built a machine learning model that does something pretty cool, like image generation, text generation. You'd want to host it somewhere, maybe build an app around it such that people can try it. Hugging Face Spaces gives you the resources that you'd want to like do that. It's pretty cool. You can like play around with other people's work here and just, I don't know, create like small games, small like fun little applications yourself. It's pretty cool. Yeah. With that brings the end of our workshop today. Thank you guys so much for your attention. And if anyone has any questions, please let me know right now. Or if you want like after the workshop, feel free to message me. I'm like active on Discord. And yeah, thank you guys so much for listening in, and hope you learned something or two today.
Does anyone have any questions? Okay, doesn't seem like there are questions.
Cool. All right. Yeah,
All right.
thank you guys again. I think I'm gonna drop off, and yeah, everyone enjoy the food, the donuts.
Who won the Menti?
Oh, yes, right. Right. Damn. Okay. So number 1, it's actually a close.
Wait, sorry, you cut out?
Can you hear me?
Yeah, you're good now.
Okay, let me share my screen just so I can see the results. Damn, I forgot